Morning, pre-calculus class. So today we want to start out with chapter 7. So chapter 7 regarding trig identity and also its inverses. So we'll start with the first sections of proving identity, part 1. So we'll start with the basic identity first. If you guys want to try some of the warm-up problems, so here's the ones like simplifying rational functions. So once you factor it out, cross-cancel or reduce, you'll end up with something like this. So now part 1. So here's the basic identity that you guys need to recognize. So one thing that we notice, cosecant is just the reciprocals of sine, secant, reciprocals of cosine, cotangents, reciprocals of tangent, and this one can be vice versa. Okay, so just flip it over, back and forth. Okay, so tangent, the ratio identity, we do have tangent of theta equals sine theta over cosine theta, and cotangent of theta, it's cosine theta over sine theta. And also we do know that the Pythagorean identity, so cosine square of theta plus sine square of theta equals 1. So that's the same as sine square of theta equals 1 minus cosine square of theta. So take the square root both sides because that's quadratic. So that's why it turns out to be positive, negative on the right hand side. So it could be positive or negative. And this one you can flip it over. So cosine square of theta equals 1 minus sine square of theta. So similar, cosine of theta equals plus minus square root of 1 minus sine square of theta. So those are the basic identity you guys need to recognize. Okay, so here's another Pythagorean identity. So we're going to do the proof later. So 1 plus tangent square of theta equals secant square of theta. And then 1 plus cotangent square of theta equals cosecant square of theta. I don't think this one is like special, like a brand new stuff for you. So this one is something that you guys already learned from trig. Okay. And now let's find out what that means, fundamental identity and applications. So a trigonometric identity, it's a trigonometric equations that is true for all values of the variable for which the expression in the equation are defined. So let's say we do have this. So secant of theta equals 1 over cosine of theta. But one thing that I need to realize, cosine of theta cannot be 0 because that would be considered undefined. Okay, so this one is just like talking about the unit circle, finding those ratios, reciprocals identity. So theta, there's certain kind of restriction. It cannot be pi over 2k because that at those positions, you'll find out that secant would be considered undefined. And then cosecant theta, quite similar. So sine of theta cannot be 0. Otherwise, you'll end up with the undefined situation. Okay, so for theta, cannot be k pi. And then cotangent of theta, tangent of theta cannot be 0. Okay, so that means, okay, let's go back. So theta cannot be k pi, where k is an integer. So those are the basic fundamental identity that you guys need to know. And now let's do some proof. Or verifying it. Okay, do not worry about the rest of this. This one just shows like a derivation. Okay, so here's another thing you guys need to know. Odd even identity. Would you know that if the function is odd, so that means f of negative x is the same as negative f of x. Even if that function is even, so that means f of negative x is the same as f of x. So here's the odd identity. So sine of negative theta, it's the same as negative sine theta. Tangent of negative theta, it's negative tangent theta. Cotangent negative theta is the same as negative cotangent theta. And also cosecant of negative theta is the same as negative cosecant of theta. So anytime that I deal with sine, tangent, cotangent, cosecant, so those are the odd functions. And here's the even functions for the trig identity. So we do have cosine of negative theta. It's the same as cosine of theta. So secant of negative theta is the same as secant of theta. We can do the proof for this, but don't worry about the proof for those identity because that's already being proved. And now let's do some practice. Okay, let me just turn on the slide. Okay, so now let's say that we do have the following. So match the trig expressions with one of the following. So what happens once you deal with secant and cosine? So secant, once again, can be written as the reciprocals identity of cosine. So it's written as 1 over cosine of x. And then cross cancel, we do have 1. So that one's pretty basic. And here's another one. So let's say we do have 1 minus cosine square of x and cosecant of x. Again, cosecant of x can be written as 1 over sine, and then 1 minus cosine square of x. So this one is just the Pythagorean identity, which is sine square of x. Or you can rewrite it as the original Pythagorean identity, combine the like terms, so we left with sine square of x. And then cross cancel, reduce the power by 1. So we do have sine of x to the first power. And now let's see what else that we have. Secant square of x minus 1 over the quantity of sine square of x. Again, using the Pythagorean identity, one of those Pythagorean identities, so which is tangent square of x. And then rewrite it with the ratios identity, or multiply top and bottom by cosine square of x. Cross cancel, put them all together, and then reduce sine square of x. So we do have 1 over cosine square of x. And using that, the reciprocal identity, so we do have secant square of x. Okay, so this one is part 1 of 7.1. So here's part 2. So this one's supposed to be 7.1, not 5.1. Okay, we'll take a look at that. So the continuation, so using the fundamental identity to simplify the expression. So sine of phi times the quantity of cosecant of phi minus sine of phi. Or people are saying that's phi. So this symbol is kind of a little bit weird. So you can pronounce it either phi or phi with the computer, symbol. So cosecant of phi, it's 1 over sine of phi. And then we multiplied it out, distribute. So this one is 1, cross cancel out. So we got 1 remain for the first term. And then for the second term, we do have sine square of phi using the Pythagorean identity. So we got sine square of phi cancel. So we left with cosine square of phi. Okay, so here's another one. So cotangent square of x minus cotangent square of x times cosine square of x. So one thing that we want to do, we want to take out the greatest common factor using the algebraic technique. And then, so cotangent square of x, so times the quantity of 1 minus cosine square of x. And then using the Pythagorean identity, once again, so we got sine square of x remain inside the parentheses. Using the ratio identity of cotangent, so cotangent is written as cosine over sine. And then cross cancel or reduce. So we got left with cosine square of x. So far it's actually pretty basic, but I would like to watch another video, the one I have for the last year, and proving any fundamental identity. And I think the other video is, the example is a whole lot more rigorous. So make sure that you watch both. And here's another one. So try to factor it using the difference of 2 squared pattern. So we got cosine of x plus 2 times cosine of x minus 2. And then find out things that they share in common, top and the bottom, the common binomial, reduce. So we do have cosine of x plus 2. Okay, so here's another one. So first thing that you want to do, looks like it's the difference of 2 squared. We can FOIL, or we can use the difference of 2 squared pattern. So tangent of x times tangent of x is tangent square of x. Secant of x times negative secant of x, negative secant square of x. Because this one, they're considered the conjugates of each other. So we can use the difference of 2 squared pattern. Or basically you can FOIL, first outside, inside, last. You'll end up with the same thing. And then using the identity, so secant square is written as 1 plus tangent square of x. Combine the like terms. So we do have tangent of x, tangent square of x, plus tangent square of x. Distribute the sign, so it's minus, minus. So they both got canceled, so we got negative 1 remain. So here's another proof, Pythagorean theorem proof. So for those you might be wondering, how do we go from 1 plus tangent square of theta? So how do we set that equal to secant square of theta? So the only trick thing that you need to worry about is the ratio identity. So instead of using tangent and secant, we're using the reciprocals identity. So tangent can be written as sine over cosine. Secant can be written as the reciprocal identity. So find a common denominator on the left-hand side, which is cosine square of theta. So convert that to the least common denominator form, and then put this all together. So cosine square of theta plus sine square of theta. So one thing that we notice, so that's 1. So we got 1 over cosine square of theta, which is the same as the right-hand side. Proof. Okay, so what does that mean? It's in Spanish, Latin, meaning which was to be proved. Okay, so here's another one. So 1 plus cotangent square of theta. Again, rewrite it with the ratio identity and the reciprocal identity of cosecant of theta. Again, using the same strategies. So rewrite it. After you rewrite it, find the least common denominator. That's right, which is sine square of theta. So convert that 1 to the same common denominator. And then put this all together, the numerator. So sine square of theta plus cosine square of theta, which is 1. So it's 1 over sine square of theta. Compare the right-hand side, which is the same thing. Again, proof. Okay, so that's it. And so please put in any comments, any questions that you have for this YouTube video. Again, I do recommend you to watch the previous trig proof video also. So the one that I put up last year for the fundamental identities. Okay, so I'll see you guys next time.